can I say about this term as t tends to infinity? So what can I say about all these terms as t tends to infinity? The system is stable, right? Stable system means all poles are on the right of complex plane. So what can I say about the exponential terms? What will happen to them? Doesn't matter whether the poles are real or complex conjugates. Doesn't matter. What's going to happen to all the terms as t tends to infinity? They are going to tend to 0, right? So since my system is stable, the plant transfer function has all poles in the left of complex plane. Okay, all poles P1 through Pn have negative real parts. Okay, so consequently, what's going to happen as t tends to infinity? All these terms will tend to 0, right? So that's what is going to happen to this term. Okay, so that's something which is very important for us. Is it clear how we got this result? Okay, so once again, I'm just using the fact that we are dealing with a stable system. So what's going to happen? So this means that limit t tending to infinity y of t, okay, which is the steady state output, right? So what is that going to be? It is just going to be a1 e power minus j omega t plus a2 e power j omega t, right? Because the third set of terms is going to tend to 0 as t tends to infinity. Okay, I hope it's clear how we got this, right? So now let's substitute for a1. a1 is going to be minus u naught divided by 2j p of j omega e power j phi, and this multiplied by e power minus j omega t, and plus a2 is going to be u naught divided by 2j, the magnitude of p of j omega e power, this is e power minus j phi, this is going to be e power j phi e power j omega t. Okay, so I think I made another small error here. This should have been e power minus j phi. Okay, sorry. Please go and correct the expression for a1. Okay, that should be minus u naught divided by 2j magnitude of p of j omega e power minus j phi. Okay, so that's what we will get, right? And now what is e power a times e power b? E power a plus b, right? So what are we going to get? So as a result, limit t tending to infinity y of t, it's going to be u naught is common, magnitude of p of j omega is common. So what am I left with? I am left with e power j omega t plus phi minus e power minus j omega t plus phi, the whole thing divided by 2j, right? So this implies that limit t tending to infinity y of t is u naught p of j omega. What's the term in the square bracket? Sine, right? So from the Euler's relationship, right? It's going to be sine of omega t plus phi. P of minus j omega. P of minus j omega is the magnitude of p of j omega times e power minus j phi. Magnitude. See, the magnitude is the same, right? Yeah. So see, because p of minus j omega will be the magnitude of p of minus j omega e power minus j phi, but the magnitudes remain the same. Doesn't matter whether it's p of j omega or p of minus j omega. Okay, that's how we got magnitude of p of j omega to be common. Right. Yes. Yeah.
As t tends to infinity, limit t tends to infinity sin omega t plus phi is infinity. It oscillates.
Oscillates. Yeah. So that's why we are finding the limit. Okay. So, you can converge to a single value because it really depends, right. So, what I can say is that this is the function to which it oscillates. Okay. So, as opposed to a unit step response of a stable system, okay, in a unit step response you will go to a constant value, right. For a sinusoidal input, if you have a stable LTA system, it will be oscillatory, okay, it will keep on oscillating, that is what we can, okay. That is the frequency response, okay, yeah.
So for a sinusoidal input, initially the exponential terms will cross some sort of
Dynamics, exactly, and then it will ultimately settle down to a sinusoid, okay. But there is an important feature here, okay. It will settle down to a sinusoid of the same frequency as that of input, okay. We are just going to look at it here, right. So let me discuss those points, right. So this is the expression for the steady state output, right. So this is the steady state output, okay. Please note that the steady state output is not a constant value here, but rather it depends on time, but it is a what is a sinusoidal pattern, right. So this is the expression for the steady state output of the system, okay. Now what is important here, right. So you look at the frequency, the steady state output is a sinusoidal what to say function, okay, but the frequency of the steady state output is also the same as that of the input, okay. So that is an important feature, right. So you immediately see that the frequency of the steady state output, or let me write it in this way, the steady state output is a sinusoidal signal of the same frequency as that of the input, okay, okay, but scaled in magnitude by the magnitude of p of j omega and shifted in phase by phi, okay, which is the phase of p of j omega, okay. That is the observation we can make, right. So from this derivation, right. Once again, please go through this derivation, pretty straightforward. Only thing is that, like, instead of numbers we just worked with general variables and functions and so on, right. So that is what we did, okay. So after from the derivation, what we can see is that if you look at the steady state output of this class of systems, the steady state output is also a sinusoidal signal having the same frequency as the input frequency, okay. That is extremely important, okay. However, the steady state output is scaled in magnitude by p of j omega. Why? Because the magnitude of the steady state output is going to be u naught p of j omega, magnitude of p of j omega. So u naught was the magnitude of the input signal, right. So magnitude of p of j omega is the scaling factor as far as steady state output magnitude is concerned, and the steady state output is shifted in phase by phi, right, because phi is the phase of p of j omega. So the steady state output is shifted from the input sinusoid by a phase of phi, okay. So that is what we have, and this is a property of stable linear time invariant systems, okay. So that is something which is very important, okay. So that is for stable linear time invariant systems, if you give a sinusoidal input and you wait and measure the steady state output, the steady state output also will be a sinusoid of the same frequency, okay. That is extremely important, and we will see that we will exploit this fact to discuss methods for the experimental determination of transfer function. Okay, and towards the end of this course we will do a case study, right. So, where I will give you data, and then like you can use these techniques to experimentally determine the transfer function. Okay, till now what the way we have been doing the determination of transfer function is through analytic means, right. So, what did we do? We essentially wrote down equations of motion, governing equations in the form of linear ODEs with constant coefficients. Then we took Laplace transform, applied 0 initial conditions, then calculated the transfer function, right. So, we will also figure out how to empirically determine that. Okay, there you will see that the step response and the frequency response are going to play a vital role. Okay, when we do that. Okay, is it clear? What is called as frequency response. Okay, so this so what is frequency response? Frequency response is nothing but the response of the system to a sinusoidal input. Okay, that's why it's called frequency response. And please note that the scaling factor magnitude of p of j omega and the phase shift phi, which is the phase of p of j omega, depend on omega, right. Depending on the input frequencies, these numbers are going to be different. Okay, so please remember that. Okay, so that's something which we will address shortly. Okay, yeah. So this p of j omega, okay, is what is called as the sinusoidal transfer function. Okay, so when you have p of s, it's a transfer function, right. When you substitute s equals j omega, it essentially becomes a sinusoidal transfer function. Okay, so how do we get p of j omega? Let us say as an example, let us say p of s, let us take it as 1 by s plus 1, right. So, that is a stable system, right. So, then what happens? P of j omega becomes 1 by j omega plus 1. This can be written as 1 minus j omega divided by 1 plus omega square, right, by multiplying and dividing by the conjugate, right. So, this I can rewrite as 1 divided by 1 plus omega squared minus j times omega divided by 1 plus omega squared, right. So, consequently what can I have? So, how can I evaluate the magnitude of p of j omega? I can do square root of real squared plus imaginary squared, right. You take the real component squared plus imaginary component squared, take the add and take the square root. Alternatively, I can also look at the function. Okay, if you have a ratio of complex functions, what is going to be the magnitude? It is going to be the same ratio of the individual magnitudes, right. So, from here I can immediately rewrite the magnitude of p of j omega to be equal to 1 divided by square root of 1 plus omega square, right. Of course, even if you do real part square plus imaginary part square, take the square root, you will get the same answer. You can double check. Okay, so you will get the same answer. And what is the phase of p of j omega? Once again, you can do tan inverse of imaginary part by real part, or you can just take the algebraic sum of the individual phases, right. So, if the ratio is 1 by j omega plus 1, what will be the phase? The phase of 1 is 0, and then since what is the phase of j omega plus 1? It is going to be tan inverse of omega, but that is in the denominator, right. So, you have a minus. Okay, so, this is going to be the phase of p of j omega for this example. Okay, so that is how we calculate the magnitude and the phase. Okay, so once again, you know, like just as a general generalization, right. So, let us say if p of j omega is going to be n1 j omega time all the way till nm j omega divided by d1 j omega all the way till dn j omega. So, what we just did was that like magnitude of p of j omega is essentially going to be just the same structure, but the individual take the individual magnitudes, right. So, that is what we are going to have. So, it is going to be this, and what about the phase? The phase of P of j omega is just going to be the algebraic sum. So, that is going to be the phase of n1 j omega plus all the way till phase of n m j omega minus the phase of d1 j omega all the way till the phase of dn j omega. Okay, so that is what we get, right. Okay, so that is what we have. Oops, sorry. Okay, so that is how we calculate the sinusoidal transfer function, right. Okay. Now, okay, are there any questions? No. Yeah, tan inverse of minus omega, we just write it as minus tan inverse omega, right. So, yeah. Okay, so that is it. Yeah, if you do tan inverse of imaginary by real, you will get tan inverse of minus omega, you just take it out, right. Of course, it is a periodic function, right, depending on how you want to rewrite it. Okay, so you will see that that's exactly my next point. Okay, now the question is, like all these equations are fine. So, from an engineering perspective, how are we going to visualize it? Okay, so that your question leads to my next topic of discussion, which we are going to continue from tomorrow, but I am going to leave you with one question. Okay, so the question which I am going to leave you with is the following, right. So how can one visualize P of j omega as omega is changed, as omega is varied, right. So, because let us say, like from a design perspective, right. So, okay, from an analysis perspective, like this is fine, right. So, we have some expressions, we have some formulae and so on, right. So, I have the sinusoidal transfer function as a function of omega and so on, right. So, now, but you see that all these are like as the system order increases, like you are seeing that the sinusoidal transfer function becomes more and more complex in structure, right. So, then like how does one interpret, right, and use it for design. Okay. So, for that perspective, from that perspective, like it becomes quite important to figure out how one can visualize, right, the sinusoidal transfer functions variation as omega is varied. Question is, first of all, we need to ask ourselves, can we visualize graphically when this P of j omega, how P of j omega changes as omega is varied? If so, how? Okay. And the answer is yes, we can, right, and broadly there are three visualizations that typically are used. Okay. So, the first one is what is called as a Bode plot. Okay. So, a Bode plot is one where there is something called as a magnitude plot. Okay. A magnitude plot where the magnitude of P of j omega is plotted versus omega, okay. But of course, on a different scale, we will discuss it tomorrow. Okay. We will use a logarithmic scale and a logarithmic measure, okay. And we have what is called as a phase plot, where the phase of P of j omega is plotted against omega, okay. So, that is the first visualization, okay. Of course, we are going to, as I told you, we are going to use logarithmic measures and logarithmic scales, right. So, we will discuss more about that tomorrow, okay. So, a Bode plot is very commonly used, okay. So, a second visualization is what is called as a Nyquist plot. So, a Nyquist plot is essentially a plot of the real part of P of j omega versus the imaginary part of P of j omega, okay, in the complex plane. Okay, what is called as the P of S plane. Okay. So, right. So we will see what this is, right, as we go further. The third plot is what is called as a Nyquist plot. Okay. So what is this Nyquist plot? I leave it to you as a question. Okay. Just search and find out and tell me the answer tomorrow. Okay. So by and large, we are going to focus on the Bode plot. Okay. The Bode plot is something which you will see that it's very frequently used in engineering applications, okay, as far as studying frequency response is concerned. Okay. So that's something which we are going to concentrate to a great degree, and we are also going to learn how to use the Bode plot for design purposes. Okay. So it doesn't matter, like what is your domain, automotive, biomedical, or even other domains, right. So you will see that like a Bode plot is something which is frequently used, okay, in the design process. So we are going to study Bode plot in detail. Nyquist plot and Nyquist plot, I will just explain what they are. Okay. So that will be the extent of essentially discussion that we will do, because we want to get into design as using frequency response, okay, for which Bode plot becomes pretty important, right. So we will start with the Bode plot in the next class, and then we will see how, given a transfer function, we can get the Bode plot of that transfer function. Okay. Then we will also ask the inverse question. If, say, through some means I give you the Bode plot of a system, right, which can be obtained through experiments, can you figure out the transfer function? All right. So that's the inverse question to ask. Okay. So given P of S, what is the Bode plot? That is something which you will learn. And then given the Bode plot, can you figure out P of S? That's a question we will ask ourselves, right? Because as an engineer, that's pretty important, right? So both questions are equally important to us. Fine, right? Okay. So I will stop here, and then like we will continue from this place tomorrow.